All right. Hello, everyone. I see people hopping in and joining. Welcome to this new training for spatial joins on Whereabouts. So happy to have everyone here. As with most webinars, we'll let everyone kind of take a chance to join and hop on. So I'll wait a few minutes to kind of kick everything off officially. But in the meantime, two different, or I guess three different things. One is that if you have any questions, there should be a Q&A section down below. You can use the Q&A to ask any questions you have of me at any time. If you're having any kind of issues or things like that, feel free to just drop a question in there, and I will make sure to get to it. Apart from that, I'm also going to send a link for the notebook for you to get started with today. So you'll download that and then load that into Whereabouts, and we'll walk through the sign up process as well if you need to get an account and get started. And then finally, as I like to do with most of these different webinars, just to get a sense of where everyone is. So if you want to use the chat just to let me know where you're joining in from, it's always good to see where people are kind of in the world. So if you want to drop that in there, go ahead. All right, Vermont, Lexington, Kentucky, South Carolina, nice. South Africa, Quebec, Bogota, United Kingdom, Montreal, San Francisco, Alabama. Welcome, everyone. All right, I'm also going to drop the link to the notebook here, so you can go ahead and grab that. You can just, you should be able to download that notebook directly, and then we'll load that in and get started here in a minute. So let's give everyone like 2 or 3 more minutes, and then we can go ahead and get started. So I'll do a quick walkthrough. I always kind of start these training sessions off with a quick walkthrough of Whereabouts, just to give you a sense of what we do and who we are. From there, we'll walk through getting you set up on the Whereabouts account. And get you kind of logged in and everything like that. And then we'll actually work through the notebook, go through the training, and talk a little bit about how to scale spatial joins within our platform. So let's just see here. Go ahead and get the full screen up. I think it looks like we're at a pretty steady level of people logging in. So let me go ahead and just share my screen, and we'll get started here. All right. So a little bit about Whereabouts. Effectively, what we do is that we kind of focus on two problem areas within geospatial analytics, data processing, things like that. The key is that a lot of stuff in geospatial is kind of constrained to a single machine, be that in a Python-based workflow, desktop workflow, spatial SQL, traditional databases, stuff like that. There are a lot of operations that don't scale, right? That's kind of the first problem that there is. And then the other piece is that existing cloud-native data lakes, a data lake being a collection of data in cloud storage, or a lakehouse, which adds a cataloging component that allows you to read and write data to that as you would a table and database. They don't support geospatial workloads. That's something we've been working on. We've added geospatial support to Apache Iceberg, which you'll see a little bit of today. And that's something we did, but realistically, that's still an area that's developing, and that's a problem that we are looking to solve. Now, if you're not familiar with Whereabouts, we're based on Apache Sedona, which is an open source project that is a functional library that brings spatial functionality to distributed computing systems. Some of those are systems like Spark, Apache Spark, Snowflake, Databricks, and Apache. I'm sorry, I'm blanking the other one, Apache Flink. So those are the ones that you can actually run Apache Sedona on. Traditionally, it's run on a Spark-based architecture for batch processing, and it's used across a lot of different organizations, as you can see here. And it's growing quite rapidly. It started as a project in 2017. It was originally called Geospark and then migrated and consistently added more and more support for raster data. We've added Python support, SQL support, and then additional formatting and structures for more like data lakehouse operations using cloud native geospatial file types and reading in data only as needed into those compute operations. Now, what Wherobots adds into that, apart from the Apache Sedona compatibility, is the speed and scale. So in Apache Spark, if you're not familiar, it's a distributed computing system. Basically, instead of one computer, you may have 4 computers that are running operations in parallel. And Spark is the orchestration system that handles all of that and the data movement and all those different pieces. Those compute nodes are not spatially aware. Now, what I mean by that is they don't account for understanding spatial relationships and spatial predicates and just how spatial data works, right? They're optimized traditionally for your normal data joins on things like, keys or strings or integers or those types of operations. What we've done is we've actually enhanced and made those individual compute instances more scalable and performant for spatial data. So that's the real key focus, is that we've built in an embedded spatial awareness. I think it's kind of like a really simple term to explain that into the compute structure. There's, of course, out of the box, data compatibility for raster and vector data. You can connect to remote data sources. So if your data is living on a cloud storage source like AWS S3, you can connect to that data remotely and only read in the data that you need, right? Those cloud optimized formats are very, very efficient. We make it more efficient to only connect into the data parts that you need and then process that and even generate, very optimized and performant cloud native geospatial data types. And then, of course, it's all serverless and cloud native. There's no infrastructure for you to maintain. You basically spin it up and you use what you use at that specific time. A little bit so in terms of like just a very high level architecture, you have the underlying spatial catalog that allows you to connect to different data sources. In like AWS S3, you can connect to Snowflake, open datasets, and then most importantly, datasets like Parquet and Iceberg. We're adding more support for different types over time. In the top level, in terms of like what you interact with in the platform, we'll be focusing on the spatial notebooks today. So that's actually like a Jupyter notebook that allows you to connect to the Whereabouts DB runtime, which is the spatial kind of processing layer that we have. And that allows you to write code in SQL and Python. We'll be using a little bit of both today, but mostly Python for the most part. And then you can also run spatial jobs that allow you to do processing jobs at scale. And there's also a spatial SQL API to use as like a data warehouse. So you can actually connect to and query us and query data at scale. Underneath that is the processing engine. So there's kind of 2 pieces to that. There's the Whereabouts DB, which is the Iceberg enabled geospatial data layer that we have. And then the compute processing layer. And then the Whereabouts AI, which is the raster inference that allows you to either bring your own machine learning model to do things like classification or object detection or segmentation with imagery data, and do that at scale in a distributed manner. So traditionally, that's all done on like GPUs, and that generally costs quite a bit. You can do that in a distributed manner and do that more efficiently, faster, and ultimately cheaper. And just to give you a sense of like benchmarking, if you're to kind of compare some different query types and how they compare to Apache Sedona running on Databricks, BigQuery, or Snowflake, you can get a sense of what that looks like here. And then there's also some other ones that we took too long. We actually had to cancel those after 24 hours. So that combination of factors, using Apache Sedona as a functional layer, using the cloud optimized file formats and connecting to remote data, reading that into Iceberg tables that are geospatially enabled, and most importantly, the geospatial enabled compute allows us to scale to this at a much larger and faster scale. So I'll pause there just to leave that at the moment. I'm just going to let's see. There was one question about where the text is downloaded. If you, I believe you're referring to the notebook itself. I'll just show you how to download that here in a minute. So you can actually download the notebook and then we can get that loaded up. So if you didn't get that notebook, I posted that in the comments. You can actually just do it as make sure it can see here. So if you go here to the notebook, just hit the download the file. You should be able to download that, figure out where it's going on your computer, and then we'll load that in into the notebook server here. So you can go ahead and save that. That's saved, I believe, to my desktop, and we'll get that loaded. So if you haven't signed up for Wherobots before, you can go ahead and sign in. Just go to wherobots.com. You can click sign in or try Wherobots. You can make an account here. What I would recommend is that if you can sign up using the AWS Marketplace, that will allow you to get access to a higher runtime, which will be a little bit more efficient for today's demo. So what I would actually do is click that. That'll allow you to sign in, and then you'll be able to run that on your AWS account. You should be able to get access to some free credits there, which will allow you to run today's demo and go from there. If not, there's the Community Edition, which allows you to access our tiny runtime. You should be able to work through, I believe, most of the things in the demos. There's one part that may not work for that runtime given the scale of the data. So just be aware of that as we go along. But if you can, try to sign up for that AWS Marketplace account. Apart from that, you can just sign up here. It'll walk you through a sign up process. Go ahead and get started with that now. And I'll do some demos of walking through the actual interface. You will have to sign up getting an email at some point to basically fill out a verification number. So it'll send you an email, send you a 6-digit number, you verify that. So just keep an eye on that, and then keep an eye on your email. And then that should get you logged into Wherobots from there. So go ahead and kick that process off if you haven't already. All right. If you have any issues with the sign up process, just let me know. Okay, there might be some folks who joined after I posted that message, so I'll just share the link to the notebook again. And there you should go from there. Once you've created your account, I'll give you a quick walkthrough of Wherobots here. So you can, you'll be logged in and you'll see this interface here. There's a few different pieces to be aware of. Most of what we'll be doing today is going to be in this notebook interface. In the notebook interface, you can see that you can select of different runtimes here that you can use for today's demo. Tiny is the smallest runtime that we have. I just reposted the link oh, sorry, here. I think can everyone see the link now? There we go. Okay. I think it was only sending it to hosts or panelists. So that was probably the issue. Okay. So there we go. So go ahead and download that, get signed up. My apologies there. I didn't realize that I was filtering who I was sending the message to. So effectively, you can take a look at these are the different runtimes that you can use. General purpose is good for most things. If you need memory optimized for sort of a large, kind of in memory for the compute instances or specialized instances, and then you have GPU instances that are built for those raster inference use cases that I mentioned earlier. Today, I would recommend using, I'm going to be using the medium runtime just for comparison, or you can use the small as well. But the medium is probably going to be the right sizing for today. But like I said, you should be able to do most of the demo in a tiny if you are on the community instance. To activate that, all you have to do is click start. There are some like advanced options here. If you want your runtime to time out at a specific time, it'll actually, even if your notebook's running, it will just stop the runtime so you're not consuming additional credits. That's a new feature that we added from before if you've been in part of these meetings before. So you can actually set that timeout to structure as you want it. And then another question I commonly get is if you need to add other Python libraries to your environment. That's actually here in this environment tab. So what you can do is you can create like a new environment, enter a name for it here. You can pick the runtime that you want to use for Wherobots, and then you can add a dependency. So you can add it. Basically, you can either add it from a file or from PyPy, and then you have to designate the version number. So in this case, if I wanted to add H5Py, I was doing some climate data work, and I have to specify the version number here just to make sure that you do that. You can't just enter a library. You have to add a version number. But once you do that, you can save a bunch of different ones. So I've saved some different ones here, and you can actually see what you can add in and go from there. So today I don't need any special runtimes. I started my notebook here, and you can see it's up and running here. So that's there. Now, a few other things I do want to point out. When you sign up, you do get access to some cloud storage. So we will be using that. This is basically an S3 bucket that you can get access to, and you can load some data in here. You can move into this, you'll see a customer folder here. And then this is your folder to add stuff to. It works in S3, which means it's very efficient for storing and reading data securely. So we give you access to that. If you want to create a storage connection to your own AWS S3 bucket, you can do that here. Just create a storage integration. I have a few. You'll just have to add in some rules here, but you don't have to do that for today's demo. We can walk through that another time. But these are some that I've created before, and I have my own storage instances that I can actually work with and access. So you can do that here if you wanted to create a new folder. You can upload here, or you can get ingest credentials. I'm not going to do that because then people could load a bunch of stuff into my account. But you can actually access credentials here, and that would give you access to load in data via the command line for like an hour there. The last thing I want to point out is the spatial catalog. So Wherobots, when you sign up, there's some open data that we have access to. We'll be using some of the data in the Overture Maps Foundation dataset and Foursquare Places. So we'll be doing some joins with those data. These are actually datasets that are stored in Apache Iceberg tables. So you can see here that if I went into the Places table, there's kind of like a catalog, a database, and then a table. You can see here that's the structure. So Wherobots open data is my catalog. Overture is the database, and then the table is places_place. And all you can see here is the structure of the table that's coming in. And then this is where the metadata is stored that stores the information about the table. What's really nice about Iceberg, and in another one of these calls I'm going to be doing that, is showing a little bit more about some of the unique abilities about Iceberg, things like time travel, as I can actually just keep overwriting a table with new data, and then I can travel back in time and say, show me this update as of this date without really doing anything else. I don't have to have like a merge and insert, upsert, stuff like that. Iceberg's really useful here. And the most important part is that it's just, all it is just Parquet files at the end of the day. It's nothing special that we're storing. It's just, optimized GeoParquet stored here that you can read in. So you can see you have some data here, and then you also have a database that we'll be creating. So we'll be creating some tables in Wherobots, and we'll actually be creating these tables here. So you'll actually see these and see the process for creating them. It's actually quite simple. So any questions so far? I'm keeping an eye on both screens here. So if you do have any questions, feel free to drop that into the questions panel. And just let me know if you're able to make it through the sign up process. You can just give me like a thumbs up or yes, just making sure we're all on the same page here and I can start to jump into the demo. Okay. Cool. All right. Thank you for that. Awesome. Okay, if you do have any issues, feel free to drop that in. I'm keeping an eye on two different screens here. So if you see me looking back and forth, that's what I'm doing here to make sure everyone's working and up to date. Okay, so the first step is once you land into your notebook interface, go to Notebooks after you've started that up and click Open. That will open this notebook interface for you to start to work with. And then we can load in that notebook. So I'm going to go ahead and find that notebook file, which I believe should be on my desktop here that I downloaded. And there it is. Let's just get rid of this. And what I can do is just drag and drop it here into this main folder. So now that I have that loaded in, we'll be able to get started. Now, there's a lot of like annotations in these notebooks, so kind of like walk you through this, even if this is your first time, kind of working with this. I'll zoom in so you can kind of see everything a little bit more efficiently here. But basically, we're doing some spatial joins, right? So we're going to talk about two spatial joins: the standard spatial join, just basically like points inside of a polygon. We'll do that both to just enrich that with the polygon name, as well as doing an aggregate as well. So kind of like a counting points in Polygon use case. Then we'll also do a nearest neighbor join, and then we'll wrap up with actually how to optimize those joins efficiently. So to start, the first thing we need to do is get Apache Sedona, our notebook, connected to our runtime in Wherobots, and that's what we'll do here. So in here, I'm just going to create my Sedona context, And then I'm going to import some functions from PySpark, which is the Python library allows us to do some different, kind of components within Python, and do some kind of SQL-based work between Spark and Python and Sedona. And then I'll basically here create this context that will connect us to our runtime. So that's probably the step that will take the longest here, is just connecting the runtime. It's just 2 lines of code, basically config that will build the Sedona context and create it, and then connect that to our notebook here. So once that's connected, we basically linked the notebook and the runtime together. Now, like I said, you can run runtimes independently via Spatial SQL. I've been playing around with building some integrations with QGIS to actually query data from your Iceberg catalog and bring it into QGIS, or load a layer from QGIS into your Wherobots database. So you can do some different things there. But that's an example of that, where we'll just kind of run the runtime, run the process, and then shut it down. But once you've gotten to this step and you see this number here, that means that your runtime is connected. Excuse me. So our first step is that we need 2 spatial data sets to do a spatial join. The 2 we'll be using today are polygons and points. Nothing too groundbreaking there. The first is that I want to pull in administrative boundaries in the US, and we'll pull that from that that Wherobots open data table here. This is a pretty simple spatial query that I'm running to filter that data. I just want the locality files, which if you look at the Overture Maps documentation, that's things like, we can just pull up, I think they have like a viewer now here for their data. Let's see here, docs, and I believe if you go into divisions, there's actually a map here that you can actually open up, if I remember correctly, Overture Maps Website Explorer. So this can kind of show you all the data that's there, and you can turn on the layers on and off. So I don't need, let's get rid of these for now. And I actually want the base files, and I want, divisions, sorry. And you can start to see if I zoom in, these, you can click these. So this is obviously like a state. You can see this is the subtype of region. If I keep zooming in, it will show me the localities. So this is a division area. This is a county. And if I get a little bit lower, then I can start to see that these are the region subtypes. And I think there's like one level lower here, which is kind of like a combination of like neighborhood, things like that. So that's locality, right? So this area, Upper West Side, is locality. If I move over here, this is also region. And then there's other ones that are like localities. So effectively, we're trying to pull in like neighborhoods and trying to get those like lowest level areas as they exist. So they exist in different areas and things like that. So that's what we're pulling in, and that's the filtering that we're doing. We're doing that for the United States, and that will load into our polygons data frame. And we'll just use that with that SQL query. And then we'll pull in a table here, which is the Foursquare Places dataset, I believe. So those are the 2 data sets that we're using. So we're pulling in polygons from Overture, points from the open Foursquare dataset. So this will just set up our query here. This will create our polygons data frame, and I can pull that in there. And then this will create that points data set, which is just the command. Instead of a SQL query, we're just doing sedona.table. Since I don't need to write a query, I just want the entire thing. I can pull that in here. And then just to get a view of the data set, we'll look at the first 5 rows. The function to use is .show. And then it will pull 20 by default, but I can pull 5 here. And you can see we have the ID, geometry, bounding box, country, version, and some other data here that comes with the polygons. And we can do the same for the points data set here from Foursquare. And these are the first, so you have a lot of different data. There's a ton of data that comes with the Foursquare data set here, and you can see all the data that's here. All right, so that's step 1. We have our table set up, and now we actually need to perform the join. Now, instead of doing this in a spatial SQL approach, I was going to use some Python functions today. So to mix it up, I know Python's probably a little bit easier for most folks. But you'll still use some spatial function predicates like st-intersects. So what we'll do here is basically, just to make things easy, we'll give our tables an alias, right? So I'll give my facilities or points data set an alias of F, and I'll give my admin boundaries an alias of poly, so I can write that a little bit faster and save some keystrokes. And then I'll do our spatial join here. So what I'm doing here is you can see that I have a join. We'll join it on our facilities data set using the .join operator. The table I want is our admin boundaries, which is our polygons. And then the expression I want to use is this. So I can actually say st intersects poly.geom f.geom. Now it's geometry, but I just shorthanded it there in the notes. And then we'll show the first couple rows of that. So now what's nice about Wherobots and Spark is basically that you don't have to actually run anything right away. As I set up these functions, nothing will run until I actually tell it to run. So right here, I'm just setting up the aliases. Nothing's happening there so far. And then to set up the join here, I'm just setting it up. Nothing's happening. And it will only run here when I run this count. I've added the time decorator in the notebook here just to tell me how long this is going to take. So I'll go ahead and run that, and it will just return the count or how many rows there are that actually fall within the intersection. So it's going through the stages here. And then once that's complete, it will tell me that it took X many seconds to complete. So we'll just give it a second here to run and go from there. So out of all the points, you can see that about 20 million of them intersected here. And that was the count. Basically, all we did was add in an additional column for the locality that it intersected onto the places table. And that's all that we did there. So you can see here the entire process took about 17 seconds in total. And then you can see here, here's the actual data set that we returned. Here's the first row just to get a preview of what that looks like. And if we have this last column here, you can see here that we have the division ID, which is the identifier of the place that we intersected it with, that locality data set in right here inside of the Overture Maps data. So that's a pretty basic spatial join. We're just taking the ID or a name or something like that and adding it to a bunch of points. But usually you want to do like a spatial aggregate or something like that. And that's where we'll get into this step here. As we go through, are there any questions, concerns, or if it's going good, just let me know. Okay. Okay, and then yes, Connie, we will have a replay as well. So we'll send that over after. It'll be sent out to you, and then we post these to YouTube so that everyone can access them too. So okay, so then the next step is we want to efficiently count points in each polygon. That's like a spatial aggregate, pretty common operation that you want to do there. And then this is the structure that we can do that. Now, of course, you can write this in Spatial SQL, but it's going to look pretty similar to what we did before. Is we're going to provide our aliases. We're going to use that st intersection, and then we have some functions here that are from PySpark that will probably look similar to something like GeoPandas or Pandas. So we're going to do a group by here. We're going to group it by the polygon ID, and then we're going to add an aggregate expression using the .ag function. And expression is count all the points as point count. And then that's what we'll do here. So there's a description of what's happening here below. But let's go ahead and run that here. So that's our code. We add our aliases once again. Poly points df, the join as the alias. It's just kind of rolled into one function here. And once again, nothing's run until I actually run it here. We can add the time decorator again here to go ahead and run this. And then we'll count how long it takes to run this count points in polygon process here. So it's pretty simple. You do have to use some SQL-like expressions here. So you can see this is count star. So it's that took 13 seconds as well, which isn't too far off from our original estimate. And then you can do these, pretty efficiently here. So you can see here, these are the IDs of the geometries and then the point count. And you can extend these functions to add more columns if you want. We'll get into that in a minute. But it's actually pretty efficient to do these kind of very large scale point and polygon counts here. Okay, so the next is the nearest neighbors join. Now, this is sort of like a k nearest neighbors join. This is a pretty common spatial question that is surprisingly complex to actually execute. Because what you want to do is for each object on each side of the table, let's imagine for a second that you are working for Zillow, right? And the question you want to ask is, what are the sale prices of any home, what are the sale prices of homes near my target home that have the same number of bedrooms and bathrooms that sold within the last 5 years, right? And get me the 10 closest ones to that. The use case here is you want to get the comparatives or the comps, I guess is the real estate lingo. The comps of your home that you're trying to sell to all the other homes with the nearest ones. Now, that's an easy question to maybe answer for one single home, but what if you want to do that join for all the homes in Los Angeles, or all the homes in California, or all the homes in the US, or the world? Who knows how many you want to do? That's where you have to add that scale distributed computing component. Now, there are ways to do this in things like Python with GeoPandas, or I've seen it done in PostGIS as well, but there's a lot of code to write. And effectively, what's really nice about Sedona is that it has this function stknn. There's two functions actually. There's stknn and staknn, which is a more approximate k nearest neighbor join, which will run a little bit faster. So to do that, what we're going to do is we're going to take the centroid of all of this is really just an illustrative use case. We'll just take the center of all those polygons and basically transform the polygons into centroids. And you can see that I'm doing that here using polygons polygons data frame, and I'm using this function select expression, and I'm selecting, basically creating two columns. The first is the ID, and then I'll create the centroid using st_centroid geometry as centroid. So now I'm going to get a table back that has two columns. One is the ID and one is the centroid. So that's the rows that I'll get back here. So nothing too groundbreaking that I'm doing here, but here's where I add that staknn. So it will have two data frames here. The first is our points data frame, or the facilities, if you want to call it that. And that represents the geometries we want to query. And then we have our centroids data frame here that we calculated just in the last step. And this is what we're doing here. So we'll have basically this is the SQL version of that. But we basically want to have the ID of the point, or the centroids, the geometries from each side, and then join them on this KNN join, right? And what's nice is I can find the four nearest values, right? The four nearest, and there's also optional other parameters if you wanted to limit it to a specific distance, like 1 kilometer, 10 kilometers, whatever. You can also limit that. And if there's only 3, it will only return free within that distance. Excuse me. So that's what we'll do. And we can do that just with a simple, couple lines of Python code here. So what we'll do is we'll say we have the alias here, Q for our points, O for our centroids, and I'll join that on this expression here, the staknn, QO4, and then false, which is that there's no sort of limit on the distance that I want to put into that. And here's my result. I'm just going to select from that data frame result the ID, the query ID, which is our our centroid IDs, the geometry centroid, and the centroid and the other geometries. And then we'll spit that out and see what our results are. So here's what we'll do is I'll create my query here. I'll add my select expression, and then this will run the entire process here. Now you can see here that there's a text warning here. One or more filter pushdowns have been detected on the object side of the KNN join. These filters we apply to the object side as it's executed. And then there's some different code here basically telling me that it will run a little bit more efficiently, but it actually ran pretty quickly. And you can see here that these first 4 rows are the same. They start with the 6DDE. These are the 4 points, and then these are the 4 centroids here that are closest to it, right? So it basically created that distance between those two. So I saw a few questions here. Does staknn use Cartesian distance between points? I'm happy to pull that up. staknn. And this one uses approximate. I don't know if it uses Cartesian specifically, but you can pass it in with a geometry of any spatial like SRID, spatial like projection, if you will. The STKNN allows you to use spheroid. So if you wanted to use a sphere, you can use a Boolean value to designate that. And then this has the search radius. So the STKNN is kind of a more approximate, which is why it's STAKNN. The STKNN can do that with a more focused search, right? So that's where that one was. And then there's a question from Vince here. Would there be a clever way to calculate the 4 in the STAKNN version, i.e. how many properties do I want, but roughly as many that are similar enough with some cap? You could write that in a more approximate way. So if you wanted to say, let's say you want to use the KNN, you could limit it by distance, and then you want them to be, let's say you have, a house that's 4 bedrooms, 2 bathrooms, and you want it to be plus or minus. You could add that into the where clause to say where bathrooms between, plus or minus the target, and then plus or minus the target for bedrooms and plus or minus the target for bathrooms. So you can add some of that logic within it. And you could basically do that. And then it's limiting to the 4 nearest. So once it hits that 4, it'll stop and say, I found 4 that match your query request. And that's what we get from there. Yves, you said you're finding something a little bit different. I without knowing what you're seeing, I don't know what that might be, but if you want to post that, I can try to decipher that over the call here. But this is, let me know if you're not getting kind of something similar to what you're seeing here. Any other questions on the STKNN, STAKNN join process? Okay. The same number of output count. Okay. As we proceed here, I'll keep an eye on the questions. So just know that I'm keeping an eye there. But I'm also going to push into oh, sorry, the first query ID. As long as there's 4 in a row, it might not be the exact specific ordering that you're seeing as mine. That might be the only difference, is that it might not be the same specific order. The table just might be ordered differently. So that seems normal as long as there's kind of like 4 in a row. So yeah, you would need an order by to keep it precisely accurate. But an order by also adds compute, extra steps to the process. So I omitted it here for that. Okay, so the last is like advanced optimization techniques. Now, there's actually a really simple step here that you can take to accelerate the join even more so than we've done so far. And all that is just kind of reclustering the table, right? So what I'm going to do is use Geohash. A Geohash is similar to something like a spatial index, like Uber's H3, S2. It's just a different approach. So you can just use Geohash. You could use H3 if you wanted to as well. It's just restructuring and re-optimizing the geometries in the table so that the nearer ones are near them. It works. It's not unlike a spatial join, but it's cheaper than a spatial join, I think is the way I would put that, without being too kind of in-depth. A spatial join or spatial index is basically a table index structure that allows you to know where things are within the table itself. We do have that capability within Wherobots, but the cluster actually gets you pretty far just by reshuffling the data. So basically, you don't know how in the table the data is structured in terms of where things are located. You could have something in New York that's close to something in Santiago, Chile, that's close to something in Sydney, Australia. This allows us to group closer geometries together and keep them optimized. So that's all we're doing here. It's a very simple optimization. Geohash, this has actually no negative like outcomes. It's actually not using, it's not joining on the spatial, it's not joining on the geohash. We're just reshuffling the data in the table based on the geohash. So within that hash, we're saying, okay, all these objects across all these tables, put those in this hash closer together in the row structure, but it's preserved, the geometries, everything else in the data is exactly the same. It's just a reshuffle, if that makes sense. So in other cases, you might turn that into a spatial index, like an H3 cell or a geohash, and join it. In that case, you could lose precision. You could, especially with polygons, as you scale up or down levels, there's overlapping issues. With Wherobots, considering we have optimized spatial compute and all these other pieces in it that make it pretty efficient to do these things, you don't have to join on spatial joins and things like that. And yeah, it's kind of like an index, but it's actually simpler than an index, right? So you could use an index to actually do a spatial index in Sedona, or sorry, in Iceberg plus Wherobots. You can do that, but this actually gets you pretty good performance just with a reshuffle of the data. And then, yeah, as Joe pointed out, there is some spatial partitioning in Sedona 1.7.1, and there's probably like a much deeper dive. Like I could do a whole section on this of like creating your files, spatial partitioning, spatial shuffling and clustering, all of those different steps, because there's optimizations you can make on the individual files. There's optimizations you can make when you're moving those into the tables. The really nice thing, and like the really nice thing about the Iceberg tables is that it adds an extra layer of partitioning on its own. So when you create the table, it actually adds an efficient layer of partitioning without you having to do any extra work, right? So I think, Joe, when you're talking about spatial partitioning, you're talking about doing some of that with creating GeoParquet files, if I'm correct. The sorting will do a more structured kind of, yeah, so this does the partitioning within the table itself, the clustering within the table. So, and there's the reshuffle. Troy asked a question. The reshuffling of the data on clustering, is that the same concept as chunking in GeoParquet? It's not dissimilar. It's not exactly the same, but it's pretty similar. You may partition differently based off of your data. This is kind of like a open debate on GeoParquet right now, but you could do that. The thing is, like with Iceberg, you're getting a bonus partition that's like not just automatically comes with it, and within that, we're saying, okay, with that bonus partition, shuffle the data to think about it spatially rather than just partitioning it the way you want, right? There's a lot of rabbit holes we can go down here that you could go down. We're talking about Upendra, when we're talking about the number of partitions here, that's more reserved for like creating GeoParquet. So I think I could definitely do a whole section on creating GeoParquet data with Wherobots and doing that efficiently. So there's a number of considerations there in terms of, kind of clustering the data, creating the partitions, compression, all of those different pieces this just does that. So all we're doing is creating the Iceberg tables here. So just to walk through the process, and maybe that'll help answer some questions. The first is I'm just creating a database if it doesn't exist. So wherobots.database name, I'm going to call it joins. Then I'm going to create my two tables here. I'm going to quickly add a column to each data frame called Geohash that has the Geohash at level 6 for the two geometries for points and polygons. And then I'm just going to sort the data and then drop that column, right? And then I'm going to turn those into the tables here. That's all I'm doing here. It's nothing, all the partitioning, all of that is abstracted away into Iceberg. So Iceberg's handling all of that for me, which is really nice because I don't have to think about it. And we're going to get a pretty good performance boost just from this one little thing. So when we're talking about creating partitions, row group sizes, compression, all of that on GeoParquet files, all of that would help on the read state and if I didn't create the Iceberg table. So I could read everything as data frames directly from GeoParquet files, and that would help that process when I'm doing those operations here, or it would help for a customer or somebody using that data outside of this, using it in, let's say, GeoPandas or DuckDB or any of these other libraries. Once I pull into Iceberg, I'm kind of entering into another kind of level here that just makes it a little bit easier for me to do. So we'll show what that looks like. So the first step is just to rehash. This is the unoptimized spatial join here. I think it was like a 13-second join, just to get a sense of what that looks like. And then we'll create the whole geohash and show what that looks like here. That's 12 seconds here. I'll just run through this process. So we'll create the database. I have it already created. I've created the new column, and then I'm going to do the sorting here. This is probably the step that might take like the most time in the entire process. Is just it's going to resort the data, get rid of my geohash column because I don't need extra data, and then create these two new tables. So I have a table here for wherobots wherobots.join.points, wherobots.join.polygons. Once again, you can see all of that in your spatial catalog here once it's created. So you have wherobots, joins, and then I have my points table and polygons, which you'll see here. Yeah, you're getting, if you get 25 seconds, that's probably because you're using the tiny runtime. So it's a little less compute that you're using there. So okay, so I'm going to pull those in just to data frame aliases, and then I'm going to perform the join here. So set that up the join. And this is with our new kind of reshuffle data here. And we'll see the join time that took 4 seconds this time. So just with that one switch of the reshuffle of the data, I went from 12 seconds to 4. And I've gotten this down to like 3 seconds and sometimes, but it's usually around that 3 to 4 second time. So it's cutting that down by 60 2/3 to 3/4 less time just by doing that one reshuffle. So it's pretty efficient just to do those simple things here. So that's the whole process here to do that reshuffling process. Now, there are a lot more optimizations that you can do. So if you go to our docs and check spatial joins, you can understand the deeper workings of this, especially from the iceberg side here. There's additional information for spatial pushdowns for joining with raster data. So there's a bunch of stuff here that you can kind of start to look at and get a sense of when you're doing some tuning. But here's the guides you can do. As you said, we have indexes. There's a bunch of different stuff you can do here. And you can look at the spatial pushdowns that you can use to create GeoParquet files, saving some of the data, sorting, which is the process that we used here. And there's some other ways. So you can add a spatial index using Hilbert to do some of that here if you wanted to. It takes a little bit more time. Then there's some options for sorting that. But just as a general, like, how can I do this quickly with the least amount of work? Sorting by geohash is like very easy to do. You can also do sorting by spatial proximity using like an S2 or any of these different things. So you kind of have to test out which one works for your data. You should kind of have a sense of the spatial distribution of your data, but there's lots of different methods to do that. Overall, you should get a pretty solid boost just by doing that sort of reshuffling of the data. Any other questions on the spatial join? Spatial join kind of process, anything like that. Any of the shuffling there. I think given the questions today, it's probably worth doing a deeper dive on the process to efficiently generate GeoParquet files. So I can certainly do that. It seems like there's a lot of interest in that topic. So good to note. And thank you for the questions because that helps me decide what we're going to do. If you want to go further here, you can. There's some simple steps to do some visualization of this data. So if you wanted to visualize this in Kepler Sedona, you can do that here. Just create a simple step to visualize that data out. Let's see here. And then there's also some steps to visualize that in SedonaPyDeck. I haven't showcased this functionality before, but it's there if you want to create a PyDeck map here and actually visualize that using a kind of a simple choropleth map. You can do that as well. But there's a lot that you can actually kind of do from the visualization side and do those different things. So I'm going to pause there because the core was on the spatial joins. If you want to actually see the results here, you can go ahead and run that code here to get that running. But I want to see if there's any other questions on spatial joins, some of the different things here. Would there be a way to do some of these optimizations as you ingest? If not, what's a good approach to not end up with huge data frames? Or is this more of a streaming process or streaming Flink process? So good question. It depends. If you're talking about like a batch data frame kind of read, making those optimizations early on in your GeoParquet files would be a good way to do that. There's probably some deeper steps you could do that in when you're reading those into Spark or things like that. But overall, that's what WherobotsDB is kind of built for, is to really be able to efficiently kind of read in and store that data and then efficiently turn it back into a data frame. So that's that iceberg kind of component. It's an open catalog, it's portable, and it adds that extra partitioning that makes it really fast. So when I read a table that I've already created in, it can do that quite efficiently. What's great about Whereabouts is I can read in spatial data from a variety of formats, from shapefiles, GeoJSONs, things like that, pull those into data frames, and then turn those into iceberg tables within my own catalog. And then from there, there's that, like I said, it kind of has that extra optimization, so it solves for some of those steps. So it's kind of, I guess the way I would put it is how much do you want to create pure GeoParquet files? If that's the goal, then there's another set of steps that you would do. But if you want to use the Iceberg catalog, that kind of has some of those optimizations built in. So you kind of get those already. Plus, there's things like time travel and stuff like that. You can actually query, just searching for the chunks of data that were added between those. You can create versions. There's a whole set of stuff that you can do with Iceberg that's really efficient. So there's that makes life a lot easier too. Plus, it has all the, kind of like DML type of stuff you would want, which is, the ability to do inserts, updates, deletes, and then you get all those histories as well. So is the spatial index transient? Could you add a little more detail to that question? And I can kind of start to, like, does the index travel with the data, I guess? Is that, or is it permanent? Is that the question? Oh yeah, it's stored persistently, yeah. So the spatial index is stored on the Iceberg table persistently, as is the reshuffling of the data. So once you create a new table with that reshuffled data, that stays there. Does some of the optimizations deal with time series optimizations like a space filling curve in 3D that caters towards XYZ? You can. So Sedona supports XYZ geometries, so the 3D geometries, and then it also supports the M coordinate as well. So if you had like there's a fourth coordinate for like ordering and stuff like that. So it does support X, Y, Z, and M, and you can optimize the spatial join based off of 3D as well. So the Z would be the M coordinate traditionally in timestamp. Z would actually be a height. So if you had X, Y, Z, Z would be the height, but it doesn't matter because it optimizes off those geometries. And you can also do some ordering based on the M, but that's embedded in the geometry, which then translates into the index and everything upstream. So yes, long-winded way of getting there to say yes. Does Whereabouts using these iceberg tables have ACID transactions? Yes. So what's really cool, and you're giving me a lot of ideas for, for new stuff here to talk about. So yeah, you can do inserts, updates, and deletes, but also I can just overwrite a table, but my history is preserved, right? So use case there is I'm creating a pipeline in Airflow, and I'm taking U.S. Water sensors. So there's these sensors that live in the rivers around the United States, and I only care about that snapshot in time. So I want my tables to show the current snapshot. I don't want to keep adding historical data and creating a really long table. But if I roll back to any view in time, I can actually go back and say what it is at that point in time and get just that snapshot of rows. So it has things like snapshot IDs, it has history, you can do inserts, updates, deletes, overwrites, whatever. And it has those full ACID transactions, which basically store in that metadata. So it's an iceberg table is nice because it's just Parquet files plus a metadata for history and a metadata for the schema. So it's really lightweight, super simple. But yeah, great question. Any other questions on joins, iceberg, GeoParquet? So it seems like and just to get a quick survey, if you'd be interested in a deeper dive on generating GeoParquet data using Whereabouts, as well as a deeper dive into Iceberg as a tool. If you want GeoParquet, if you just want to quickly type GeoParquet, if you want Iceberg, type Iceberg, or both, just type both. That'd be really helpful for me to get the right thing. Okay, awesome. So we can do that, and that will help me kind of inform me what to build going forward. But I'm glad at least today was helpful. I know we're wrapping up on time. I just want to see if there's any other final questions. Otherwise, I just want to say thank you all for joining. If you have any questions, you can reach out to us. If you just go to our website, there's a chat bot down at the bottom. You can start asking questions and get connected to us with someone there. If you want to email me directly, my email is just matt@wherobots.com. So feel free to reach out with any questions that you have. And if you have any specific use cases that you're trying to solve and you want to, actually get us, set up some time and work through that together, happy to do so as well. So just reach out there. I'll just, one more time, I'll drop my email so everyone has it. And yeah, feel free to reach out. But thank you everyone for taking the time to join. And I have some work to do on my end for our next sessions. So thank you for all the engagement and the questions. That really, really helps us build the right stuff for you going forward. All right. Thank you, everyone.